All right, welcome back from the coffee break. We're kicking off with a presentation by Niklas Gustavsson, the Chief Architect at Spotify. Within Spotify, his primary areas of focus encompass holistic architecture, technology innovation, engineering practices, and a keen interest in advancing data-driven architecture. Niklas will now delve into the topic of a data-driven study of our large-scale microcomponent architecture. Niklas, welcome to the stage, and thank you for making it to our event.
Thank you, and thanks for having me. See if I can get my slides up. Oh, here we go. Cool. So yes, I'm Niklas, and I work at Spotify. So today's talk is actually inspired in part by last year's conference. So last year, there was a theme on how to measure architecture. And there was a lot of questions around how to apply those practices to a more modern microservice architecture. So I'm going to talk a little bit about how we do that at Spotify today and some of the patterns that we're seeing emerging within our architecture. This morning, we also saw Mark talk about best practices for microservice architectures. And we'll see to what extent that we fulfill those good patterns or not. We can talk through that. Cool. So let's kick us off. So to begin with, Spotify is actually yesterday celebrated 15 years, and we stumbled on a microservice architecture from the very beginning, not because we were particularly clever or were able to foresee the future, but the folks that started out Spotify, this was a year or so before I joined, they had this idea that based on the Unix principles of having things that do one thing and do them well and then combine them together, that would function also when building an architecture. These were a bunch of folks straight out of university that had never built a production service before. So they made a pretty lucky bet over a bunch of beers, I think, in an evening on how the architecture should work. And since then, we've actually been able to scale that up, and I'm going to talk a little bit about that, what that looks like today. And in fact, pressing the wrong buttons. We also apply this to things that are not services. So every component within our software ecosystem is built on the same set of principles as you would imagine a microservice architecture. So reasonably small, decoupled components, much like Mark talked about this morning. So this is important. So we apply this across the board. So if it's a data pipeline, if it's a website, if it's a module that goes into our mobile apps or whatnot, they're all built in the same way. Each component being owned by a separate team. I'll talk about this in a second. And basically take this pattern that we have found successful in our backend and apply that across the board. And this is what it looks like in this highly abstract model. So on the top here, we have our teams. We call them squads. And each of them owns a number of what we call systems. So systems is just like a logical group of then components. A component might be a backend service, might be a data pipeline, might be a micro frontend type of website. Combine up to a system. We'll look at that in the next slide. And then, of course, we deploy these into our production environment in many, many instances. We will not talk that much about that part today. So let's take a look at a practical example. This is a highly, highly simplified picture, but for our reasoning today, I'm going to use this. So let's imagine that we're looking at our playlist system, Spotify's music audio streaming service. Our users and ourselves produce these playlists. We store them into this playlist system, and users can interact with them in various ways. So you can imagine that we can separate this into, there's a playlist feature that might live in our mobile apps, and then there's this playlist system or playlist platform that lives in our backend and in our client. So we provide client-facing APIs within our clients to make it easy for our mobile developers to build features on top of our playlist system. And you can see a number of different components here. So there's a playlist service, there's the library that runs in the client, and there's the actual front-end view of this, all modeled into this notion of small components. And again, each of these being owned by a separate team. And when I say owned, the ownership goes from the very early beginning of Which components should we have? What product are we actually building? To designing, implementing, and operating that. So a team owns the full life cycle of their components, and they themselves make the decisions on which component they need, how they should be connected together, and so on, which means that in practice we end up with a pretty emergent architecture. It's not that myself or someone else sits and like from above points and say, hey, we should have these components. We let our teams decide that in a pretty distributed way. All right, so now let's get into the actual topic of today. How can we make this measurable? So I'm going to claim that for many, many years, Spotify, I'm going to extend this and say the industry at large, has mostly taken architectural decisions based on hunches and gut feel. And we want to shift that to become much more data-driven. You can imagine in a large-scale architecture like ours, and I'm going to talk a little bit more about that, it's hard to have a good hunch. It's really hard. I used to pride myself many years ago in that I kind of understood which systems we had, which backend services we had, how they fit together. That is no longer the case, and it's no longer possible. We're at that scale. Mark said this morning that, and I think this is a good reminder, you are not Netflix. Unfortunately, we are kind of Netflix, so we have to deal with what that means. All right, so I'm going to walk you through a little bit on the work we've done to make our architecture measurable and look through a few examples of what that looks like in practice. So first of all, how do we actually measure things? So we use a combination of signals. Those might be declaratives. We might, we ingest our source code so we can analyze that. We have this developer portal that we call Backstage that we've open sourced. In Backstage, every component is registered. We ingest that so we can use that data. We have our org structure, lots of these declarative type of data sources. And then we instrument our actual runtime. So we use Kubernetes, we instrument what pods are running in Kubernetes, which component do they belong to, which dependencies do we have between different components, all our builds, all our deployments, all those types of things. So we have lots and lots of these different data sources. We take all of those and we put them into Google's BigQuery, which is this ad hoc queryable database that can manage very large scale. So we have that data all in a single place that we can, any developer and any employee at Spotify can query and analyze. So this is somewhat simplified, but you can imagine a query looking something like that. So in this case, we're looking at how many components does a particular owner, a squad or similar, have. And in this case, we're looking for data pipelines specifically. And then you can extend these types of queries to look at different properties of the source code, different properties of the components, how they're deployed, all the dependencies they have and whatnot. And everything we're going to look at today comes from a query looking something like this. Nope. All right. Don't know why that stopped working. All right, so let's talk through our sort of high-level look at what these components look like in practice. So on the top here, you can see the growth in the number of production components that we've had. It's not entirely true. Back in 2020, we didn't have that few components, so you can see a little bit of an effect that we've been able to improve our instrumentation over time. But I think what's interesting with this graph is that currently in production, we have 13,000 unique components. So there's something like 3,500 different backend services in order to power Spotify. There are roughly similar number of data pipelines and so on. So it takes a lot of software to run a large-scale and sort of feature-rich service. You can maybe look at this and say, like, what the fuck are you doing? Like, this looks insane, and we'll look at even more insane pictures in a second. The thing is, if you compare ourselves, like we've compared ourselves with the Netflixes and the Metas and the Ubers out there, all of those architecture looks very similar to ours. So this is what these very large-scale architectures look like in practice today. At the bottom, you can see the number of lines of code in these services, the average of that. So this is just to illustrate like what does micro mean in practice. And you can see that across the board, with the exception of mobile, our components average is around 3,000 lines of code. That the 3,000 number is not particularly important. I don't actually know how we ended up with like this kind of even average. That was not intentional by any means. But having the components be relatively small, 3,000 lines of code, is something that you as a developer can sort of understand and reason about. That's the property that we want to get to. So if you would imagine putting all of this into very large monoliths, and we've had a few of those over the years, it makes it much harder to reason about them. Again, Mark, I think, did a good work of like talking through the different properties that might motivate you to split something into separate services. We use the same set of principles. The mobile being an exception here is a side effect of the way that we do dependency injection on mobile, so that's not a particularly interesting number. If you would look at the sort of more meaty actual components that we use, they tend to be similarly sized. So I talked about our ownership and that every component is owned by a squad or a team, like your normal agile team, like 5 to 10-ish people. And you can see that this is just looking at ranking them on like how many components does a single team own. So you can see that on average, a team, or in the median, I should say, owns 6 of these production components, which is probably roughly sane for a team to be able to manage when they do on-call and so on. There are definitely outliers. You can see that there's a single team that owns 300 components. Those components are sort of auto-generated. They're where we do a multi-tenant type of hosting of things. It's not as crazy as it might seem, but you can see that there's a lot of different patterns for different teams. All right, so let's switch over to talk about deployments. And one of the main reasons why you might go for a microservice architecture is that you want to have this like alignment between component and the owner of that component in order to allow that team to deploy their stuff without depending on everyone else, right? So that's probably one of the properties that you want to get to. Get away from having to orchestrate or coordinate a bunch between teams and have each team run their own deployments. Ship when they are ready to. So then you can say, so one of the things that would indicate that this architecture is working is, have we been able to scale the number of deployments as we've grown as a company? So that would be a good signal for us. And in fact, we have. So this graph shows the number of deployments we do. Currently, we do around 2,600 deployments per day. Each team that works on a component typically will deploy that component multiple times per day. And they can do that, again, without coordinating with anyone else. And that means that we can reduce the time, we call it outer loop cycle time, so the time from you starting on a task or having an idea to shipping that into production. And for our backend services, for example, or data pipelines, that's on the order of a few hours today. So you can go from like starting to code, go through code review and CI build and deployment and be live within a few hours. And this is true for new services, true for the service that's been around for 10 years. Another trend that you can see in this particular diagram, the purple-ish line shows the number of deployments from human authors, so our developers, and the gray line shows the number of deployments that are triggered by automation, different types of bots that we use. You can see that that number has quickly ramped up over the last few years, and that's due to an investment into something that we call fleet management, where we're trying to automate the maintenance of our components to a much higher degree. And we expect that number to go up further. So in a few years, we expect that we will have many more deployments from automation than from developers. And that helps reduce the amount of toil that developers has to do. So rather than, keep your frameworks up to date or fix security fixes or fix reliability fixes, we can roll those out across the fleet and automate those deployments completely. But the important point here is that we have been able to, like I said, scale up the number of deployments as we've scaled up the company. So it's not that by growing and becoming larger as a company, we're getting slower, which is a very common pattern for companies. All right, so let's talk about dependencies. This is where I sort of spend most of my time thinking about this stuff. So you can imagine in this, and wait for the next slide, you have a pretty complex set of dependencies between your different components. And the dependencies, just a reminder, it's these like curvy lines here. So when you have a backend service and you need to access playlists, you're not going to rebuild your own playlist system. You're probably going to call into that playlist system that I showed before. And now you created a dependency on that. You are a backend service calling another backend service. Or if you're a data pipeline, you're probably dependent on some upstream data sets. Like you might be joining a few data sets, do some data processing, and output another data set. Now you have a dependency on those upstream data sets. And we collect these dependencies by primarily instrumenting our runtime again. So within our data processing infrastructure, we record like every interaction of a data pipeline like that. Like, oh, the infrastructure ran a pipeline, it used these upstream data sets, and it produced these downstream data sets. Now I know that there's a dependency between the upstreams and the downstream data sets. Hopefully that makes sense. And for backend services, we record like what services are different, what services does a particular service call into, and who calls into that service. And we record all of that, stick it into BigQuery, as I mentioned before, and we can do all types of analysis on that. And what does this look like in practice? So this is the dependency graph of backend services at Spotify. And Mark again talked about the big ball of distributed mud. You could definitely argue that this is that. So I think this graph shows a few interesting things. So yeah, sorry, each dot in this graph is a unique backend service. So somewhere in there is a playlist backend service, for example. Each edge in the graph is a dependency between one backend service and another backend service. One service calling into another service. And the size of the nodes is just of like how central is this node in this graph. How many things is calling into that particular thing. So the playlist service that I've been using as the example is one of our more central services. I don't actually know which one is the playlist service, but it's probably one of the larger nodes in here. So the point of this diagram is obviously to sort of illustrate the complexity of an architecture like this. You need to have good ways of managing your infrastructure, have a good understanding of your components, have a good understanding of the dependencies between those components. But it also shows that we're able to get a pretty high level of reuse within this system, and I'll show you that in a second. You can, of course, also make a good argument for that this is probably a pretty hard system to change. So if we would want to make holistic changes to this, it's a lot of dependencies to untangle in here. On the flip side, it's fairly easy for us to replace and split each of these nodes, and we do that frequently. So we might re-implement the service, or we might split the service based on the principles that Mark mentioned this morning, for example. And that's relatively easy because the dependencies here are only on API definitions, right? So they're not actually dependent on the actual implementation of that service. So we can re-implement the service or make changes to it. And as long as we maintain API compatibility, no one else is going to notice in this graph. So the playlist system that I've been using as the example, in practice, it's called Playlist 4. And that's because we're on the 4th generation of that service. So over the years, our early designs for that just didn't scale or whatever it was. So we replaced it by a new implementation. And we can do that again because we can replace nodes in this graph without affecting the overall graph. So in practice, if we look at our dependencies, each component, backend service, pipeline, mobile component, whatnot, on average depends on 9 downstream components and are depended on also by 9. So you can see that, again, we're getting a lot of reuse through this architecture. And another way to plot this is you can plot it like this. So this is just, imagine on the x-axis are every component, and on the y-axis is the number of number of components that depend on that component. You can see that you get this very, there's a few components that are very popular, gets used a lot, and then there's a very long tail of components. And then when you see a graph like this, the classical thing to do is to instead plot this on a log-log scale. And if you do that, it looks like this. And if you squint a little, you can see that this is roughly a straight line. And if you do statistics on it, it actually is a straight line by statistics. And one of the properties of when you have a network that looks like this, it's called a scale-free network. And one of the properties of scale-free networks is that you should expect that you will, as you grow the network, you get more and more popular nodes in that network. So you have like preferential attachment, I think it's called. And for us, that's important because when we think about the reliability of our dependency graph, like if we have an incident, what will be impacted in that? We can reason about that we will continue having more and more important systems from a reliability perspective, that we need to be particularly careful about how we design them, how we operate them, and so on. So this is one of the metrics that we keep an eye on. And you can plot this in a different way. So each of someone called this a fireworks diagram, which I liked, but so each of the bursts in this fireworks is one of our, we call them studios, so they're a collection of squads, like they're a team of maybe 50 to 150 or 200 people. So each of them are plotted here on the, the left-hand side are the things that they provide that others are dependent on, and on the right-hand side are the things that they depend on from someone else. Hopefully that makes sense. So you can see these, for example, these large ones in the middle, you can see that they have few dependency on others, and they provide a lot of stuff for other teams. And these are two of our main infrastructure squads. So they provide like our runtime infrastructure, our data infrastructure, and so on. So that's exactly what we expect from those organizations. We want them to have few dependencies because these systems need to be super highly available. So we don't want them to have a lot of dependencies on other stuff. And they provide functionality to the rest of the company. So this is exactly the type of pattern we would expect to see. And then on the flip side, you can see studios like this, which have a lot of dependencies, but are not very dependent on. And these are typically the teams that work on our end user features. So they will produce the playlist view that I used in the example before. And not a lot of other teams depend on their functionality. Their primary users are our end users, but they, of course, depend on a lot of functionality from others. So they build on that infrastructure that we talked about, or they build on that playlist service and whatnot. So again, we can use this to reason about different properties of our organization and how we should set up operational capabilities or whatnot within our org. All right, so this is maybe the hardest, I'm sorry by killing you by graphs today, but this is probably the hardest graph to read, hardest graphs rather. So the left-hand graph here shows these dependencies again. On the x-axis and y-axis, you have every team. So every column and row in these diagrams, it's not super hard to see that there are columns or rows, but you can imagine that there are. Each of them is one of our teams. So we have 600-something teams. And depending on the intensity of the color, they have more or less software dependencies on each other. That's the left-hand diagram. So if we're you and I are in two different teams, and I'm calling your backend service or I'm using your data sets, I have a dependency on you, and there's going to be a dot in between you and I here in this graph. On the right-hand side, we're seeing the same thing, but instead we're seeing pull requests. So you can imagine, again, if we go back to the software dependency, if I have a dependency on your backend service, I might be sending you a pull request because I might need improvements or changes in that backend service. And there are three things that might be worth noting in these diagrams. So at first, you can see that there's a very clear diagonal going through the graphs. This is a good property. So this means that we have more dependencies within our teams than in between our teams, and we'll look more on this in a few slides. That means that our org structure is probably roughly correct. Org structures are never fully correct, but at least it's not crazy broken. And again, like we actually want that to be the case. Like the people that work closely in a team, they should be collaborating a lot and probably have a lot of software dependencies on each other, while someone who's in a completely different part of the org should have less dependencies on each other. You can see that there are a few clusters in here as well, where there are larger sets of teams that works more closely together. You can see that there are these clear vertical and horizontal stripes in this graph. Those shows like the popular services and popular components internally, where some team provides a platform that many other teams uses. So, for example, I keep using this playlist service because it is one of those like popular internal platforms, and one of the stripes that you will see in here is on the team that owns that playlist service. Hundreds of other teams uses that, and now you can see all of those dots shining up. And the third observation that is interesting here is that you can see that these two graphs kind of look the same, and that shows that we have that correlation between if you have a dependency on each other, a software dependency on each other, you will also collaborate more. You will send each other more pull requests back and forth. And this is kind of intuitive. You could imagine this being the case, but this confirms that at least for us that is the case, and that means that we can optimize our organization based on that, so we can make sure that teams that have these dependencies on each other, they can easily collaborate together because they're close enough in the organization or whatever we want to do. It also means that we can predict future collaboration. So if we're creating a dependency today, we know that those teams will likely work together in the future. So again, we can use that to help inform how we organize ourselves or how we work together. All right, so let's look at two practical examples of how we've used these metrics. So the first one is going to be on mobile. So I mentioned before that we've had our experiences with monolithic software as well. One of those was that we ended up building both our mobile apps, both on Android and iOS, to be highly monolithic. And a few years back, we sort of ran into the wall on we couldn't ship very effectively on that because we have had all of these tightly coupled dependencies between teams. So we ended up with just a lot of coordination. So over the last few years, we've been on this effort to decouple our mobile code bases. And one effect this high coupling had was that it was very slow to build our mobile apps. It would take hours to run it in CI or run it locally. And the apps are a bit north of 1 million lines of code each. So you can imagine that takes some time to build. And because they weren't modularized, you had to build all of that typically and whatnot. So we started breaking that down into smaller modules, but we weren't getting the effects on build time that we were hoping. The lower graph here shows the build time as it's ticking up. And the reason for this, and this is where this dependency data came in handy, because we literally have tens of thousands of these dependencies within our mobile apps. And you can see, and this is not going to be surprising to you, there's this anti-pattern of a library that is used by a bunch of dependents, and it has the API and the implementation in the same artifact, and every time we make a change somewhere in the dependency graph upstream from this API, we get this explosion of things that we need to rebuild. Everything needs to be rebuilt. So every time we make a change up there, we have to rebuild a huge part of our code base. And this, of course, when you have to rebuild a large part of the code base, it's going to be slow. So what we did instead was to decouple these two. Again, this is just standard inversion of control or dependency injection, nothing magic here. But the hard part is when you have tens of thousands of these, how do you even go about trying to figure out where to start? And the way we did that was that we used this dependency analysis and basically put it into a graph analysis tool, and we could start working through and see which should we start with, which of these libraries will have the biggest bang for the buck in terms of our build time, and then start working off them in that order. And that was exactly what we did. And in a year or so, we ended up with a 10x improvement in our build time. So this is it's a very, as you can imagine, a huge improvement as a developer. If you have to wait like 30 minutes or 3 minutes, is a pretty big difference in order to build your app. If you're interested in this, there's a talk that we gave at BaselCon, I think maybe a year ago now, that goes into much more detail on how we did this. You can find it by Googling. It's a great talk by two of our engineers from our mobile infrastructure org. All right, so let's look at the other example. And we already alluded to this a little bit. I'm sure you all know about Conway's Law. It's this law back, I think it's from the 60s. And it states pretty simply that whatever way your organization looks like is also how your technology is going to look like. And this, I think, has been identified as sort of a law of nature at this point. It's very hard to not end up in this pattern. And of course, the typical interpretation of Conway's Law is you don't want that to happen. You want your architecture to be independent of what your org structure happens to look like today, but it's very hard to not do that. And one way to think about this is to reverse that. So think about it in terms of, if that's going to be a fact, what should our architecture look like? And that's again where like these micro-component architecture comes into the picture, and we can try to optimize and make sure that we have the right ownership for those components. It goes back to that heat map I showed before. Like, we want to optimize where those dots shine up so they are aligned with our org structure. The closer teams are in the org structure, the easier it will be for them to work together. They will have more shared incentives, more shared priorities. So we can look at how we're actually doing. So one way of measuring this, there's, again, if you use graph theory, there's this metric there's called modularity. We're used to thinking about modularity in software architecture. So modularity, this is somewhat simplified, but you can imagine counting the number of dependencies that you have, software dependencies that you have in between your teams, and divide that by the number of dependencies that you have within your teams. And you don't want to strictly optimize to only have internal dependencies, because you do want to reuse things from other teams, right? We don't want every team to re-implement the playlist service. So we don't want this to go to zero, but we probably don't want it to go to infinity either. We don't want it to only be external dependencies. So there's some trade-off that we want to find here. And we can turn this into a metric, and we can plot that, and for us it looks like this. So this is this modularity metric over time, and you can see that it's slow. The trend is sort of slowly creeping up. So we're getting more and more modular in the way that our org is set up. And this is based on we're getting slightly more aligned with in between our software ownership and how our org structure looks like, which is a positive sign. You can see that there's a lot of ups and downs in this graph, like it's pretty wiggly, and those changes are due to when we have made ownership changes. So when we moved some number of components in between teams, like we might decide that this team is better set up to own this problem, or this is a feature that we're going to decommission in the future, so let's put that on a different team. Or where we are making organizational changes. So if we change the way our org structure looks like, we might also be changing our modularity. And again, we use this metric to inform, is this a good way to reorganize ourselves or not? So you can actually start predicting we're discussing to set up our org in this structure instead. Would that improve or screw up this metric? And where you screw it up, you can then start compensating for that. All right, that's it. So just wanted to say, this is still very much work in progress for us. We're very actively working on exploring different set of metrics. I've only shown a very small set of metrics here today. We are finding that we need to continuously improve our instrumentation. So I talked about how we instrument our runtime and how we inject all of these declarative data sources, but we find continuously that there are rooms for improvement in that, and we find gaps in our instrumentation, and we try to work those off over time. And we've found that these metrics can be pretty useful in how you think about your architecture, how you make decisions for your architecture, and even inform things like how we set up our org structure and how our teams can work better together. And with that, oh, that was the wrong order, wrong direction. And with that, I'm super curious how, first of all, if this makes sense for you within your context and your architecture, and where you have experiences of measuring things within your microservice or microcomponent architectures, would love to learn from that. So ask questions now, or I'm going to hang around for lunch as well, so please feel free to come up to me and ask questions and give feedback. With that, thank you very much for having me.
Thank you for that, Niklas. Very interesting to know how you do it in Spotify. So we have a lot of questions again. And actually, 30 people voted for the first question that I will ask. So let's say a billionaire buys Spotify and renames it to Spotify X. How many components could he delete without the system breaking down? Or, paraphrasing it, how many components are important for the core business?
Yeah, it's a great question. So I guess this is the Muskian question. So I can't actually answer with a number. It's definitely so that if you look at that dependency graph that I showed, not every node in that graph is equally important. And we have a tiering system where each owner assigns a tier based on the criticality of that component. So I don't know the numbers off the top of my head, but I could look at like how many tier 1 systems do we have, how many tier 4 systems do we have, and start trying to answer that question. What I think for backend services, I mentioned that we have around 3,500 unique ones in production. I think, if I remember correctly, that we have a few hundred tier 1 services. So that's probably roughly the order of magnitude of like, we would be fine with reducing down the feature set of Spotify and not report any financials or not have any payroll systems to pay our employees and whatnot. That's probably roughly what we could get down to. Like we could operate the core of our service, make sure you can stream audio or interact with your playlist or whatnot with a few hundred services. But of course, a lot of the one sort of fact about a company like us is that we don't know what we're doing. We're trying to build a service that no one has built before. We're going to get a shit ton of things wrong, so we do a lot of experimentation. So many of the services that you see in here is some type of ongoing experiment that we might or might not keep for the future. And our teams build many of those experiments. They run lots and lots of A/B tests to try to figure out if this feature is worth having, is this improvement worth having, and then that might go into becoming a tier 1 system, or it might be decommissioned. So that's worth knowing. Like this is not a static picture. There's experimentation and changes going on every day. That's why we're doing thousands of deployments every day as well. So if your goal is to create the minimum static Spotify, you can do that with a substantially smaller subset. But that's not the business we're in, so that's why it looks like this. Hopefully that's a useful answer. Sorry for not having an actual number.
Niklas, you're an absolute champion so far. People are super aligned, and more than already 29 votes for the first questions.
Good.
So people are really interested in knowing the answer to the question. So 2,600 deployments a day. How do you solve coupling changes in one component affecting other components?
Yeah, so this is another question where I don't have a good answer. So, like I said, we're making these thousands of deployments every day. We have that crazy, complicated dependency graph. And you can imagine it would be frequent for us to break backwards compatibility in a way that would break large parts of that graph. You could then further imagine, in order to protect against that, we would do a lot of testing to compensate for that. Do a lot of like consumer contract-driven testing, things like that. We don't. And somehow this works anyhow. And that's why I don't have a really great answer to this question. Of course, we do a lot of integration testing. So when you make a change to your backend service or your data pipeline, you will run that against a set of integration tests that will, spin up another downstream service in a containers and your own service running a container, make sure that they can interact with each other. You might stub out that service to simplify your testing. Somehow that ends up working, and this is something that honestly still surprises me, how little of those compatibility breaking changes that we end up having. We do have strong conventions around how we do API design to minimize the risk for non-backwards compatible changes, but we don't do a particularly great job at testing for those breakages and still have a fairly low frequency of them. That's the unfortunately uninformed answer to that question. It just works, I guess.
Thank you. Okay, the 30 votes go to a question. Can you explain the difference between the service and component from your point of view?
Good. This is a good question that I probably should have explained more carefully. So component is our core entity when we think, let me take this one step back. So we have this way that we think about how we model our software. So it's actually defined internally. We have something called the ecosystem model, software ecosystem model. And in that model, we essentially have a domain model for how to think about our architecture. And the core entity in that model is the component. So when you register something in our Backstage portal, that is your component typically. And that's what we have these like tens of thousands of. And there are then different types of components. So if you would draw a typical class diagram, this would be a subtype of a component. And there are many different such component types. And the most common ones are like a service, which is something that runs in our backend, typically with a request-response type of API over gRPC or similar. And we have a data pipeline, which is something that typically runs on a schedule, like every hour or every day. It depends on a set of upstream data sets, and it produces another set of data sets. And we have websites, you can imagine what they might be like, and we have these mobile components. Mobile is a little bit special because our mobile apps are built up by these small components. Again, they have API dependencies on each other. But what's different about mobile is that end of the day, they all ship as one big monolithic binary every week. So we ship our mobile apps weekly, and to do that, we have to package together all of these components into that big app that we end up shipping to the app stores. So the way that we work with mobile is pretty different from everything else. So when I talk about these thousands of deployments and them taking typically a few hours, that's true for everything except for mobile. For mobile, it typically takes about a week for someone to ship changes to our users. We would, of course, like to improve that, but we're somewhat constrained by the app stores. I don't even remember it's component and service. Hopefully that clarified what it is. So service is a type of component. Let me continue quickly on that. So then we group components. So once you have thousands of components, it's really hard to reason about them. And if I'm a developer, I'm going to continue using the example of playlist, and I'm a developer, I want to call the playlist API. I don't actually care about exactly which services they have. Like I showed that diagram of the playlist system, and it had like 3 services in it or something like that. In reality, the playlist system is something like 15 different services. I don't care about the details of that. So we have a higher order of abstraction, which is just for like humans to understand our software. That's what we call a system. And a system is just a grouping of a set of components. So we have the playlist system. And the playlist system exposes a set of APIs. So if I, again, want to call into the playlist API, I can just reason about there's a system for playlists and don't have to care about the internals of this. The previous speaker spoke about C4. It's very similar. Like the the properties that we're trying to get to is very similar to how C4 has those like different levels of abstraction. And in fact, we have a mapping from our ecosystem model to C4 and use C4 for a lot of modeling that we do. Yeah, I think that's roughly it.
Perfect. Is there a master team managing the big picture who decides, approves new retiring components?
No one is the answer. So there's no master team, there's no one who overlooks all of this. There are people like myself that try to make sure that we're running roughly in the right direction. So we set up guardrails for architecture. So there's a lot, like, guidance for how to build things or whatnot. But end of the day, it's each of our teams that are empowered to make the decisions on how to design our software. And we put a lot of trust into them doing that in a sane way. So yeah, there's no one approving new components. There's no one having a grand master plan for what this dependency graph should really look like. It's a very emergent architecture. And that definitely has pros and cons. It gives you a lot of downsides in terms of you don't always make sane decisions. Every now and then we do something bonkers, and then we have to deal with that. And on the positive side, you reduce a lot of coordination between your teams. There's no one that has to go to someone to get that new component approved and wait for that approval. They can actually ship that. You can literally go from creating a backend service and having that running within production in an hour. And that's a very powerful thing, is if what you're trying to do is to run these experiments that I talked about and learn very, very quickly. So that's what we're trying to optimize for. It's a great question. It's a super hard trade-off to make. And I think for different companies and different industries, you're going to want to optimize differently. If you're in a heavily regulated industry, for example, you are surely going to want to make different decisions than we have made, for example. And if you're a startup, you probably want to have less guidance than we do and even more freedom. So you have to figure out where on that trade-off scale to place yourself.
Thank you. What's your testing strategy for your architecture? How much do you rely on end-to-end tests?
Sorry, what was the last part of the question?
How much do you rely on end-to-end tests?
Yeah, so we have a lot of test automation, but they are primarily on component and integration level. So of course, we have a lot of unit testing for our components, and we have a lot of integration testing where you test one component and with its immediate dependencies, perhaps. We have very little end-to-end testing because it sucks. Like, it's super hard to do end-to-end testing and keep those tests viable and valuable. We have done end-to-end testing over and over again. Like, we keep reinventing that, we should do end-to-end testing for this. And it quickly breaks down. In this like fast-paced, ever-changing architecture, it's really hard to keep end-to-end tests up to speed. We still have some end-to-end tests. We have, I mentioned like being in a very regulatory industry. We're not in a heavily regulated industry, but we do have some like financial regulations and so on that we are under. And in those cases, we have more end-to-end tests, and they are a pain in the butt. So wherever we can do our testing in a way that aligns with this notion of having small components that are relatively isolated, the better we're off. So again, this is somewhat unintuitive, I think. Like when you look at these dependency graphs and look at this number of dependencies, it's easy to imagine that I'm going to want to have a lot of testing that spans across this chaos. But it turns out that that is, at least for us, not worth it. We don't discover enough. Those tests break much more frequently because things has changed in a good way than in a bad way, and that's not a good property of a test.
How do you handle component ownership change from team to team? How often does it happen?
Another great question. You're good at this. So yeah, so that's a very frequent thing. I don't actually have an up-to-date number, but I remember I looked at, I think it was like 2021 maybe, and we did 500 ownership changes, something like that. So 500 components that changed owner. So that means that every day there's multiple of those ownership changes going on. So it's a very frequent thing for us to do, and it's not without pain. As you can imagine, like taking over something that someone else has built, there's going to be a lot of onboarding and learning activities in that, and you're going to, I think a natural human property is that we consider anything that someone else has created to be crap. So there's a tendency for us the new owner to want to rewrite the thing they just took ownership over. So this is actually we actually track, I didn't show this today, but we actually track this as a different metric. So we have a metric called knowledge loss. And it's basically what share of the code base in a component was written by someone who's no longer in the owning team. And that can be because you've changed the ownership of the component, then you're basically going to go to like having 100% knowledge loss. It can also be from natural things like people moving between teams, people leaving the company, whatnot. So this is a metric that we keep an eye on to make sure that we're not having part of the company where we have a very high level of knowledge loss, because if we do, we know that we have to spend more time with those teams to educate them on the software they now own and so on. And we've actually had that. So we've had teams that have ended up with a very high degree of knowledge loss, again, because of some critical people leaving, or them taking over ownership of a large share of components, for example. And when that happens, we know that we have to give those teams more time to absorb that ownership. So we try to deal with it in that way. The other thing we are very intentional about is that we have limited the amount of technologies that we use. So I mentioned that we allow our teams to decide how to design their systems and how to run them, but they do that on top of a shared infrastructure. So we deploy things into the same runtime environments, we have the same application frameworks and whatnot, and that is something that one of the guidance that we give to your teams, to our teams is, if you're building a backend service, this is the service framework you should be using, this is the way you should deploy that, and so on. And that means that when you actually do one of these ownership transfers, the thing that you're gaining ownership of is going to look roughly the same as the things that you already have. It's going to run on the same infrastructure, it's going to use the same frameworks, the same patterns, and so on. There's a lot of flexibility within the application part of that, so we still get that behavior of, like, I'm going to rewrite this crap, it looks nothing like what I'm used to. But we limit that, and we lower the cost of doing ownership transfers.
And last question. With 13,000 components, do you have some system that will detect unused one?
No, unfortunately. So these are awesome questions. You're finding all the sort of weak spots here, so it's great. So I just mentioned like a minute ago how you can go from creating a backend service to having that running in production within an hour. And that was, for a long time, what we optimized for. We had this method, and it's a good, quick aside. As everyone knows, when you have a set of metrics, like I've been talking about today, you get what you measure. And this was a great example of that. So we were measuring the onboarding time of new engineers. And one of the properties of that is like you need to make it very easy to bootstrap a new component, make it easy to create something. And we did that. So in Backstage, we built all of these like cookie cutter templates for what a new component would look like. We automated how to create those. So you literally go in, fill out a few properties, like what's the identifier of your component and who's the owner and whatnot. Press the create button, and that thing is running in production in 2 minutes. So that's what creating a new component looks like. The flip side of this is one thing that we did not optimize for was how do you decommission a component. And this is still something that we're struggling with. So we have now built the infrastructure to do that decommissioning. So there's a similar button you can press and it will remove everything. So it will go around and clean up your cloud environment, cloud resources that you have for that component, and remove it from CI and do all of that infrastructure stuff. But the question asked, like, how do you know if a component is unused? And that is a super hard question to answer. you can, for us, it shouldn't be, but it is. So you can do some basic stuff, like you can go in and you can check if, like, what's the RPS that I'm getting to this backend service, or is someone reading my or consuming my data set on some regular interval. You can get those basics, but typically what you will find is that, yeah, you still have someone calling your backend service, like, and who the fuck is that thing, and how do I get them to move to something else? Like, that whole process of, like, efficiently decommissioning components, we have not nailed. And again, we have a metric for this that I also didn't include. So I have a metric called decommission rate that I track, and it basically measures, if you compare this month to last month, how many new components have we added versus how many have we removed. And we are almost constantly above 1 on that ratio. So we're almost constantly adding more than we're removing. And you could see that. I showed a graph of the number of components before, so you can see that effect in that graph. And it's natural. We're still like a growing company. We're running many experiments, learning and building new features. So we would expect that to continue being above 1, but we want to make it much easier and cheaper to and lower risk to decommission a component. I think I'm out of time. This was great questions. So if you have more, feel free to come up to me at lunch, and I'm happy to discuss more.
Thank you so much, Niklas. It was incredibly interesting. Thank you.